let's talk a little more about the self-ionization of water. So we talked about the fact that water self-ionizes, which means a reaction that has two like molecules react to give ions. So we have our water reacting with another water molecule, and one proton from one water molecule is transferred to the other water molecule. That's what happens. So we get our hydronium ion in solution and our hydroxide ion also in solution. Okay, and then we talked about the ionization constant or the equilibrium constant of water. So K is our equilibrium constant. W is of water. And when we work that out, we get the concentration of hydronium ions times the concentration of hydroxide ions. Okay. So that number equals 1.0 times 10 to the negative 14th. And remember, for equilibrium, it's temperature reliant, so that's at 25 degrees Celsius. Here's a little trivia for you. Kw at body temperature is 2.5 times 10 to the negative 14th. So there's some trivia for you. Okay, we can use this equation and this constant to figure out the concentrations. We can calculate the concentrations of hydronium and hydroxide in pure water. So in pure water, we're going to have exactly the same amount of hydronium ions as hydroxide ions. We can call them X. What do we want to call it? But X is going to equal hydronium ions, the concentration of, and it's also going to equal the concentration of hydroxide ions. Okay, so if we plug it into the formula, so we plug X into the formula, we could say X squared equals, since these are both going to be equal to X, 1 times 10 to the negative 14th. Calculating for X then, X therefore is going to equal 1 times 10 to the negative 7th, which equals, so we're going to substitute in, hydronium ion, and that's also going to equal our concentration of hydroxide ions. So that's where we get our 1 times 10 to the negative 7th for each. Okay, now what happens if we add a strong acid or a strong base to water? So let's just say we dissolve 0.1 moles of hydrochloric acid in 1 liter of solution. Okay, so we would end up with a 0.1 molar hydrochloric acid solution. So we want to know what's the concentration of the hydrogen ion or hydronium ion in this solution. So we have the self-ionization of water, but we also have the reaction of hydrochloric acid with water, which also produces hydrogen ion. So this only works with strong acids and strong bases. There's a whole nother situation for weak acids and weak bases. So let's write out our reaction. Hydrochloric acid in solution, aqueous, reacts with water to produce hydronium ions and not hydroxide. What's our other ion going to be? Chloride ions in solution. And we could write that without the water, which is fine. So since we started with 0.1 mole of a hydrochloric acid in 1 liter of solution, the reaction is going to give us 0.1 mole of hydronium ion. Or, I mean, if we want to simplify this, we could just do this, because then we would just get hydrogen ion and chloride ion in solution. Either way, we have 0.1 mole of our hydrogen ion. So the concentration of the hydrogen ion is 0.1 molar. So that's going back to understanding complete ionization and ionic compounds, and we talked about that in a different video. So we have 0.1 molar as our concentration of hydrogen ion from the hydrochloric acid. Don't forget, we still have the ionization constant of water. So that's still going to self-ionize. So we need to consider that, the concentration of the hydrogen ion produced by the self-ionization of water. So if it was pure water, our concentration of hydrogen ion is 10 to the negative 7th molar. So in a solution where acid was added, this contribution of this particular proton, this hydrogen ion, from the self-ionization of water is going to be smaller. So we added acid to water. That hydrochloric acid is going to add a lot of hydrogen ion. Water, from the self-ionization of water, is going to add a little bit. Okay, now we want to look at how much. So the contribution of this hydrogen, concentration of this from water, is going to be smaller than 10 to the negative 7th. Okay, so hang tight. We're going to apply Le Chatelier's principle to see why this is going to be smaller from the water portion. So we added acid to water. So why is this going to be smaller? Well, here's our self-ionization or auto-ionization of water. At equilibrium, we get hydrogen ions and hydroxide ions. Okay, so it's going to have to balance itself out. So if we're adding hydrogen ion to water by adding an acid to it, so now we're adding this, it's going to shift our reaction to the left until we get back to equilibrium, which means the concentration of this produced by the self-ionization of water is going to be much smaller and really negligible compared to the concentration of the hydrogen ion that's at, we already know it's at 0.1 molar. So in a solution of a strong acid, you can normally ignore the self-ionization of water as a source of hydrogen ions because it's so much less, and that really should make sense. The hydrogen ion concentration is really determined by the strong acid. Okay? So unless we have a really, really dilute solution, we can use the auto-ionization, the Kw of water, to calculate the concentration of the hydroxide in this situation. So we know we have 0.1 molar hydrogen ions from the hydrochloric acid. Okay, so from the last slide, we already know this. Okay, figured that out, not a problem. Now the question is, how much hydroxide is left? Because it's still there. There's just not a lot of it. So a question could be, calculate the concentration of hydroxide ion in 0.1 molar hydrochloric acid. So it may be an acid, but there's still some hydroxide ion in there because there's some water in there. So we can substitute this into our equilibrium expression and just solve for hydroxide. So our equilibrium expression, Kw equals the hydrogen ion times the hydroxide ion. Kw is 10 to the negative 14th. In this example, hydrogen ion is 0.1 molar. And we're going to solve for hydroxide. Well, when we do that, hydroxide is going to be a very small number. So rearrange the equation, divide both sides by 0.1, and our hydroxide ion concentration, even though it's a strong acid, it's in there because it's in water, is 1 times 10 to the negative 13th molar. Let's consider an example of adding a strong base. So consider a 0.010 molar sodium hydroxide solution. What are the hydroxide and hydrogen ion concentrations in this situation? Well, if we break apart sodium hydroxide into its ions, it's a 1-to-1 relationship. So if we have 0.010 molar of this, that means we have 0.01 molar, there should be another zero in there, molar hydroxide ions. So that takes care of our hydroxide ion concentrations, 0.01 molar. So we have that. Now, to solve for how much hydrogen is in there, because it's aqueous, so it is a solution. Again, I was making assumptions. So consider a sodium hydroxide solution. We can use our Kw to solve for the hydrogen ion concentration. Hopefully by now you know it's going to be really small. So 10 to the negative 14th is our Kw. We don't know our hydrogen ion concentration. We do know that our hydroxide ion concentration is 0.010 molar. Divide by 0.01, and our hydrogen ion concentration is going to be 10 to the negative 12th. Okay, I want you to keep these two examples in your minds when we move on to talk about pH and concentration of hydronium and hydroxide ions.